Good afternoon, everyone, and welcome to this executive briefing from Nanostone Water. I am joining you from the Dubai office of Nanostone. My name is Atman Shah. I'm the Director of Business Development. And today we are going to talk about ceramic ultrafiltration membranes and the advantages of using these membranes for pretreatment of seawater RO. We are going to talk about the technology features and some of the case studies, especially in seawater pretreatment globally and in Middle East. Um, I extend warm thanks to all of you to taking out the time and making it to this executive briefing. I hope at the end of this presentation we can have a good interaction, and thank you again. Nanostone is a German manufacturer of ceramic ultrafiltration membranes, and our headquarters are in the USA. Nanostone has a full-fledged office here in Dubai, which is catering to the Middle East and African region. As most of you know, seawater RO operations tend to rely on robust pretreatment. If the feed water to the downstream RO is free from suspended solids, turbidity, and organics, typically RO membranes have an extended life of up to 7, 8, or even 10 years, and the cleaning of RO membranes can be extended to as long as 1 or 2 years. However, due to the recent seawater quality, conventional RO pretreatment has often struggled, and this has resulted in challenging feed water going to the RO. This results in the plant having capacity loss, high frequency of RO cleaning, and of course, reduced life for the RO elements. The ultrafiltration membranes of the polymeric type were implemented to address these issues. In terms of seawater quality today, there are a lot of challenges with respect to algae blooms, be it red tide or green tide. There is a high variability on the inorganics due to the tidal effect. And more importantly, the concentration of organics has substantially increased. As I've mentioned, polymeric ultrafiltration membranes were implemented almost 15, 20 years back to address these issues. However, polymeric UF has been successful for surface water treatment or river water treatment, but has not been suitable for seawater, simply because it allows the pass-through of organics or dissolved organic content, and there is subsequent carryover to the RO because the fibers of the polymeric UF often have integrity breaches, they break a lot. There have been cases where the flux has to be derated during the variable feed water quality, and this not only impacts the overall capacity, but also is a loss of revenue. The challenges that I'm sharing or mentioning are not only a regional issue, but today a global issue. And there are facilities, there are operators which face these challenges throughout the globe. There have been capacity losses, there have been derating of flux, there is frequent cleaning of RO elements, which leads to higher downtime. All in all, plants often operating at subpar conditions than design. Looking at the current shortfalls, the current challenges, it is safe to say there is a lot of room for innovation on pretreatment for seawater RO. Historically, in addition to the polymeric UF, dissolved air flotation or DAF was implemented to address and combat some of these challenges. However, DAF by its own has issues with respect to poor organic removal, a poor micropollutant removal, and DAF, as you know, is a very civil intensive process requiring a lot of construction time and, of course, requiring a huge amount of footprint. This is where the nanostone ceramic UF technology can come into the equation to address these issues. Because of the unique design and engineering feature, which I will talk about shortly, we are able to eliminate the need for DAF, media filtration, sedimentation, and even cartridge filters. So the pretreatment operations are streamlined, the complexity of the pretreatment is reduced, the number of steps required for pretreatment to RO are reduced. So this is the advantage of the ceramic ultrafiltration. The cost on a system basis can be significantly reduced. The ceramic UF of Nanostone is a pressurized ultrafiltration, which is an extruded support plate, as you can see on the left image. It's a segmented plate design with 2.4 millimeter feed water channels. These feed water channels, because of 2.4 millimeter diameter, maximize the water transfer efficiency, and the pore size of this membrane is 0.03 micron or 30 nanometers. The material uses aluminum oxide, which has free-flowing electrons maintaining a negative charge, which always can be changed depending on the cleaning. Because of the wide feed water channels, we handle a high concentration of suspended solids, particulate matter, and of course, solid algae matter. And because of the nanoparticle ceramic coating on the surface of the membrane, it gives us a very tight pore size of 0.03 micron, and by which we can deliver consistent filtrate water quality for RO feed. Moving from the technology details, we want to talk about some of the recent case studies in seawater pretreatment, specifically starting with Southeast Asia. We partnered with PUB in Tuas, Singapore. PUB is Public Utility Board, which is responsible for providing drinking water for Singapore. They have multiple large-scale facilities with different pretreatment methods, ranging from DAF, conventional media filtration, and of course, conventional ultrafiltration, which is fiber-based. However, the quality of incoming seawater was often challenging in terms of algae blooms, turbidity, which was to a degree impacting their existing facilities. So PUB was looking for a pretreatment solution which is much more robust and provides dependable RO feed water quality at all conditions. We started working with PUB and completed a 1-year demonstration, a pilot demonstration, which was installed in parallel to their main plant to have a real-time comparison. The data coming out of the pilot was a success. By inline coagulation dialed in with the ceramic UF, that helped us balance the DOC removal and the membrane performance. We tested our inline coagulation at different pH conditions. At pH 5, which is enhanced coagulation, we found a relatively high concentration of DOC removal, organic removal, but also at the same time, a relatively high concentration of metal organic complexes, which get precipitated on the surface of the membrane and therefore slightly impacting the TMP. However, by doing a sweep coagulation at pH 7, we could see a relatively stable delta P or TMP, and of course, a relatively good DOC removal in the range of about 50%. The inline coagulation is always recommended because it helps us form a pre-coat layer on the surface of the membrane, and this not only traps the silt and the suspended solids, but also embeds the organics into the pin floc. At 2 hours, we tested at different fluxes for our ceramic UF, starting from as low as 100 lmH, as you can see in the light blue, and as high as 300 lmH. And we found that the long-term demonstration, the optimal flux should be 250 lmH. We had our first algal bloom during the month of October. And as you can see on the 150 lmH, the delta P, which is represented by the blue color, the delta P slightly increased during the algae bloom, where the chlorophyll was about 40 parts per billion. And just by doing a simple chemical backwash, we were able to restore the permeability back to normal, as you can see on the rest of the section. This was very interesting because we did not have to do a intervention, or we did not have to do an offline cleaning by cleaning in place, CIP. We continued our demonstration, and we were at 250 lmH, and we had even a more intensive algal bloom where the chlorophyll levels reached 60 ppb. And again, as you can see, there was a marginal increase in the delta P. And again, by doing a chemical backwash, we could restore the permeability. So at both instances, this was very encouraging because we did not have to do a CIP. We did not have to put the system offline. All this during very high turbidity of 40, 45 NTU and high SDI of up to 5. We could still maintain a recovery of 98% and a total uptime of 97%, with CIP frequency of 3 months and a chemical backwash frequency of once every 24 hours. Our ceramic UF membrane also has a good tolerance to oil. In the case of 2Us, there was upstream injection of marine oil to the extent that we were receiving about 1.2 milligram per liter of oil, and fairly good tolerance, as you can see on the graph, on the permeability and the flux. And we could achieve a filtrate oil of less than 0.1, which is basically 80% removal without instantaneous fouling. Conventional UF, as you know, tends to foul instantaneously when there is oil, but the ceramic UF could sustain such an oil concentration. The other case study that I want to talk about is in Barka, Oman, with private developer Aqua Power. They have an existing RO facility with incumbent conventional membrane filtration process. The Gulf of Oman is very challenging, as you know, shallow sea waters combined with frequent algae blooms resulting in high organics and suspended solids. Again, we started working hand in hand with the operator and the developer, installing our ceramic UF pilot in parallel to the main plant, again, to have a side-by-side comparison. We tested at different regimes and fluxes and found out that looking at the very aggressive water quality and the fluctuations in the water quality, that 150 lmH was the ideal optimized flux for a long-term demonstration. There were frequent algae blooms, especially in the month of March, April, where the SDI 15 was more than 6, and the chlorophyll levels reached 50 ppb, sometimes even more than 150 ppb. And even during the fluctuating water quality, we could maintain the performance and the uptime, and at the same time delivering an outlet STI of less than 1.5 and a filtrate of a turbidity of less than zero point 0.5. Again, inline coagulation was always dialed in, um, and depending on the water quality, the adjustment can be made, but we always recommend inline coagulation, typically with ferric chloride. As you can see, at a flux of 225 LMH, we had fairly stable permeability, the key operational parameters fairly stable. At 200 LMH, we also saw a reduced delta P across the several filtration cycles. And for the long-term demonstration, we selected 150 LMH, which was fairly stable. There was a particular event in March where there was a severe algal bloom, and because the coagulation was not dialed in, the right dosage was not dialed in, we could see a increase in the delta P, as you can see on the dark blue side. But once we were able to dial in the coagulation, we could maintain the permeability by keeping the same flux, as you can see for the rest of the month of April. So the algae bloom persisted even in April, but we could maintain the performance by dialing the coagulation. In a nutshell, in a summary, the Nanostone ceramic UF offers promising solution. It combats the challenges and the shortfalls of pre-treatment technologies today. And more importantly, it can improve the reliability and productivity of seawater RO plants at all seawater conditions. It allows to reduce the capital expenditure by eliminating multiple pre-treatment steps, as I've mentioned at the beginning of the call, and it has tolerance to oil and grease, and at the same time can remove up to 70% of organics, which can not only enhance the RO downstream, but also improve the performance and life of the RO system. With that, I am thanking each one of you to attend again this executive briefing, to hear about Nanostone technology and our case studies and our success stories. I would like to now open up the floor, the platform, for any questions or comments or feedback from you. And I'd also like you to download this Nanostone desalination brochure, which you can see on the right-hand side on the screen. It talks about the technical and commercial benefits of Nanostone for pre-treatment of seawater RO. And if you would like, you can schedule a one-to-one call with myself and the Nanostone team to talk about how we can support you for your upcoming projects, for ongoing projects. So you're welcome to schedule a call with me with the Calendly link, which is showing up right now. Thank you. Please go ahead and post your questions. Okay, so I'm gonna start taking some of these questions which are popping up. Let me start with the first question, which is our existing pilots and additional new pilots are in operation now. So thank you for that question. Yes, our Kobar pilot, which is an agreement with SWCC, it is going to be a long-term demonstration to test the ceramic UF effectiveness for Arabian Gulf seawater. The pilot is being installed at the moment, and we are expecting the operation to start sometime in August of this year. We'll be happy once we generate data to share those data with each one of you. Thank you for that question. The next question is if I can elaborate a little bit about what I mean by CIP in 3 months. So thank you for that question. Um, Casting back to the case study I was talking about to us in Singapore, because of the long filtration cycles, typically of 90 minutes, and the chemical backwash frequency optimized for just once every 24 hours, we are able to maintain the flux and the permeability without having to do a CIP. In other words, the ceramic UF is able to have high availability, and by um, extending the frequency of CIP to just carry out CIP once every 3 months. So that's the benefit, the long extended filtration cycles, the ability to maintain the permeability and delta P without having to do a CIP more frequently to restore the permeability. So we could optimize this in the case of 2 hours, where we have to do a CIP once every 3 months, not before. The other question that we received is the type of oil that was encountered, whether that was free floating or emulsified. We did not have a bifurcation in the case, specifically whether it was free floating or emulsified, but we did have a concentration of about 1.2 milligram per liter. Okay. The other question, which is just popping up, is what is the CEB regime and the CIP regime? Thank you for that question. The chemical backwash, or the CEB, is typically combined with sodium hypochlorite caustic, followed by a low pH acid cleaning. The CIP typically consists of the same chemicals, but in addition, we use citric acid depending on the nature of the foulants, the nature of the fouling. But all in all, it is standard chemicals. We do not require any special chemicals for CEB or CIP. Um, we've touched based on this before, but I don't mind taking it again. The question is, what is the tolerance of oil? So as I've mentioned in the case of Tuas case study, at the upstream of our ceramic UF, that is the feed to our ceramic UF, we had an oil concentration of 1.2 milligram per liter, and the filtrate oil was less than 0.1. So we remove or reject up to 80% of the oil without having instantaneous fouling of our membrane. The other question is during the CIP process, whether the plant or the system will be offline. Yes, typically during the CIP process, the system will be brought offline, and the cleaning in place will be carried out. But the objective here is always to have a high availability of the ceramic UF pretreatment system. As I was mentioning, at the case of Tuas, we could have an online availability of 98%. In simple words, our demonstration lasted for approximately 1 year, and during those 12 months, we had a 98% availability. And this is simply because we could extend the CIP frequency so that we just have to carry out one CIP every 3 months. And only during that specific duration of CIP, the system has to be taken offline. The duration or the time needed for the CIP is again dependent on site to site, case to case. It is usually an overnight soaking, which lasts anywhere in between 4 hours to 8 hours, depending on, again, the case to case, system to system. Okay. The other question is, what is the lifespan of this ceramic membrane? So, the ceramic membranes of Nanostone are engineered for a 20-year lifetime warranty. Um, so, the manufacturing defects, integrity breaches, etc., are all covered for a period of 20 years. We offer a 20-year lifetime warranty, contractual warranty. Um, this is an interesting question, and I'm happy to see this. What would it take for Nanostone to bid for a project without doing piloting and going straight to a commercial installation? Well, this is where Nanostone is today. We've gone out, we have confirmed the proof of concept, we have validated the technology for very poor seawater conditions, as we have spoken about Barca, Oman, to Singapore. And to further prove that concept, as I've mentioned, we've signed an agreement with SWCC. We are going to start piloting soon at Al Khobar on the Arabian Gulf. But historically, the Nanostone Ceramic UF has close to 90 commercial operating installations with a total operating capacity of about 400,000 cubic meters per day, handling complicated water and wastewaters. So we are today ready, going straight to commercial installation because we believe that no matter the water quality, the ceramic UF of Nanostone will be a solution, um, which is a perfect fit for your upcoming projects. Thank you for that question. Another question is whether pretreatment like DAF is required, especially in a case of algae bloom condition, or is it possible to directly feed to the ceramic UF system? Yes, absolutely. If you cast back to the schematic of my presentation, by streamlining the pretreatment options, we are able to remove DAF, media filtration, sedimentation, lamella, and cartridge filters. All those multiple steps can be removed, and a direct ceramic UF feed or direct intake filtration is possible with our membrane. And another question is that specifically for the organics removal, whether the ferric salt is the chemical to be used. Yes, typically for seawater applications, as you know, the preferred technology is RO. And considering that in mind, we recommend ferric chloride. And we've also found ferric chloride to be much more effective in trapping organics and micropollutants for seawater applications. On the other hand, for surface water applications, it really depends on the customer, on the site requirements. We have commercial operating plants where we are using different coagulants, sometimes using aluminum-based coagulants and sometimes using ferric-based coagulants. So for surface water, yes, we are using different chemicals. For seawater specifically, we have found ferric chloride to be much more effective. Another question is during the variation of turbidity and suspended solids, how does the ceramic membrane behave? So, as I've mentioned, we have a feed water channel which is 2.4 millimeters. So it's a very wide feed water channels that allows us to retain and hold incoming suspended solids, particulate matter, turbidity, solid algae matter, and because of that, we have filtration which happens across the length of the module. In other words, we have a very high retention volume by across the length of the module and the 2.4 millimeter channels. That gives us the highest retention of solids and thereby giving us extended filtration cycles up to as high as 90 minutes. So because of that, we are able to have steady state operation, steady state flux and permeability, even when the turbidity or the suspended solids are increasing during an event. Another question, which is it possible to have ceramic UF installed inside a container for a commercial plant? Absolutely. It's possible. We have operating references globally where our ceramic UF system, along with the peripheral equipment, along with the auxiliaries, have been installed in a container, and these have been running for a few years now. So yes, we have the design, we have the standard design, and we would be happy to send over those details and the case study, especially for a containerized commercial plant. We understand that containerized solution can be a good solution for footprint point of view for sites where area is a constraint, and we are doing this, as I've mentioned, for coal mining customers. We are doing this for surface water, drinking water projects, and yes, it is possible to do that for your commercial plant as well. Another question is, in addition to the turbidity handling question, what is the maximum turbidity levels that can be handled by the CUF, the ceramic UF? Thank you for that question. Um, we have industrial wastewater references, again, operating references, where the incoming turbidity, average turbidity is about 4,000 NTU, and the peak turbidity is in the range of 8,000 NTU. This is an industrial wastewater reference where our ceramic UF has been able to handle this turbidity without any issue. Talking specifically for seawater, in the case of Tuas, the incoming turbidity during the tidal fluctuations was as high as 45 NTU. And as you saw from the performance graphs, we had no challenges whatsoever. In the case of Barka, Oman, especially during the algae bloom, the turbidity sometimes was more than 30 NTU, reaching sometimes 40, 45 NTU. And again, was not a problem for the ceramic UF. We did not need a DAF, a media filtration, or even a micron strainer before our ceramic UF. So that's the maximum turbidity. Basically, there is no limit as far as suspended solids or turbidity is concerned. Another question which has just popped up is, and sorry, by the way, if I'm not doing this in sequence because they are coming as I'm taking them one by one. So sorry if I answer your question a little late. Uh, a question I just see right now is a cost comparison between ceramic UF and PVDF UF membranes. Well, as I've mentioned, the biggest advantage of ceramic UF is that multiple pretreatment steps can be reduced. So the cost on a system basis can be optimized and can be reduced. However, on a one-to-one comparison between ceramic UF and PVDF, of course, Of course, the ceramic UF is more expensive simply because the life of the ceramic is 20 years, whereas the PVDF membranes typically offer 5, 6, or 7 years. So the advantage here is that we don't need DAF media filtration, and that's how we are competitive on a system basis. Another question is what is the treatment required to dispose the backwash water of the UF? The wastewater that is generated from the ceramic UF is typically no different than the conventional processes, whether it is the conventional media filtration or a polymeric ultrafiltration. So it can be the same approach, it can be the same system that you have to dispose of the normal filtration backwash water. Another question is whether our system operates on a dead end mode or a cross flow mode. Well, typically for seawater applications, given the energy efficiency, which is an extremely important aspect for all stakeholders, we typically operate at a dead end mode, which means whatever we feed, we produce. However, in very specific applications like industrial wastewater or water where there is an extremely high concentration of suspended solids, in those specific case, that might be possible to have a hybrid, which is having 70 to 75% dead end mode, while 20 to 25% can be cross flow. But that is only in the specific cases of industrial wastewater where there is extremely high TSS. Typically for seawater, we do a dead end filtration. Another question is whether we have tried to use PaCl, polyaluminum chloride coagulant. Um, well, for seawater, as I've mentioned, ferric chloride has been found to be most effective. Of course, many of our industrial wastewater projects are running today with PaCl. Um, in general, we've found PaCl to be more effective on industrial wastewater, uh, while we have found ferric chloride to be more effective on the seawater side. Okay, I do hope I've answered your questions. I'm sorry if I've missed any of your questions. Please don't, I would encourage you to repost them just in case. Okay, another question is what type of strainer or ASF? Um, I'm assuming that's an automatic self-cleaning filter is what is required before the ceramic UF. Um, yeah, so we do not require a micron self-cleaning filter. All we need is a 1 millimeter screen. 1 millimeter or 1000 micron screen. It it can be any type depending on the system integrator's requirements or the client's requirements. We don't have a preference as such. All we need is a 1 millimeter fine screen. Another question is if we have dosed an oxidant in addition to coagulation on the pretreatment side. Yes, in the specific case of Barca, Oman, owing to the fact that there was a very high concentration of biofouling potential and organic potential, we did find continuous chlorination to be much more effective as compared to non-chlorination. So, of course, the facility has some amount of intake chlorination or shock chlorination, but in addition, a continuous chlorine stream helped us maintain the TMP at all times, even during the algal bloom events and variable feed water quality. Another question is if we have a smaller model than CM151. Well, at the moment, this is one module which fits all applications. So this is what we have, our standard model CM151. I think the follow-up question for the chlorine is that how much chlorine did we dose? We were typically in the range of about 2.5 to 3 ppm. The objective here is to maintain a residual chlorine content. The idea with the ceramic UF process is that the growth or the proliferation of bacteria should be controlled. And by doing a continuous chlorination, we break down the organics. The macroorganics get broken down into microorganics, and these microorganics are much, much easier to be trapped with the inline coagulation, the ferric chloride. So that is how we remove the organics. And continuous chlorination helped reduce the TMP because most of these organics are a precursor, are a source of food for the bacteria. So if you can control the organics, you can control the biofouling. And that's how, by dialing in inline coagulation along with chlorine, we could have a significantly higher reduction of organic fouling and biofouling with our system. We're just about at the end of the hour. So I hope I have answered your questions, your comments, and I do apologize if I've missed some of the questions, but please feel free to schedule a call on a one-to-one basis, or please send me your questions, information over email, and I would be happy to answer them. The Nanostone team is always at your disposal to provide you robust, sound pre-treatment solutions for your seawater projects. Again, thank you for taking out the time to attend this executive briefing. We hope to see you in the future. Thank you so much.